guys, in this video we're going to look at deriving the derivative of the inverse sine function. So we're going to just do a quick start by looking at the function for sine of x itself. So you might remember from pre-calc that this is the graph for y equals sine x. And if we wanted to try to find the inverse of a function, it's supposed to be 1-to-1. Which means that it's supposed to pass this horizontal line test. And we can tell that since sine domain goes on forever and it oscillates between those values, that it fails that 1-to-1 test. So what we do is we have to restrict the domain for sine so that it is 1-to-1. So they happen to choose this interval right here so that we get all of those y values from -1 up to +1 and never cross through them a second time. So they're restricting the domain for sine x to go from -π/2 to +π/2. And that would make my y values go from -1 to +1. Now, if we think about the definition for an inverse function, the definition for an inverse function tells us that the inverse function of x is equal to y, then that means that f of y is equal to x. You may have been just taught, if y is equal to sine x, to find its inverse, you just switch your x and y's around. So we can then say that x is equal to sine y. Now, if we want to find the derivative now, what we can go ahead and do to find the derivative of this function is just use a little implicit differentiation. So I can differentiate x to get 1. And then differentiate sine y to get cosine y times that derivative of the inside dy dx. Now, when I look at this, I can now see that there's my dy dx. There's my derivative for my function here. So I can go ahead now and divide both sides by cosine y to isolate that dy dx. Now, when we're going to look through this, we want to get our derivative of y in terms of x, and right now it's still in terms of y. So we're going to go off to the side and do a little bit of review from pre-calc. So you might remember your fundamental identities, those Pythagorean identities that we always used a lot in pre-calc. So sine squared y plus cosine squared y is equal to 1. I can, since my derivative over here uses cosine y, solve this equation for cosine squared y by subtracting that sine y to the other side. And normally when I would solve, I would need to take the positive or the negative square root of our function. But because we're restricting our domain here, and we're looking at our values for cosine, from -π/2 to π/2, our values for cosine are always going to be greater than or equal to 0. If you think about your unit circle, from -π/2 to π/2, the cosine or x values are always over on this side, so my cosine values are always positive. So when I go to solve and take the square root for this specific problem right here, based off the domain we're working with, cosine y is equal to the square root of 1 minus sine squared y, and we're keeping that positive square root. And then another little trick here is we've already said that sine of y is equal to x, so we can go one step further and say that that's equal to the square root of 1 minus x squared. So then we could go back over here now, and if that's what cosine y is equal to, then we can say that our derivative is equal to 1 divided by the positive square root of that quantity of 1 minus x squared. And in this function right here, remember, we were working with x is equal to sine y, so we were working with the inverse function. So we can now say that the derivative of that inverse function, so the inverse of sine, we would write as sine to the -1 of x, is equal to 1 over the square root of 1 minus x squared. And again, that's going to give me on the domain for x, because when we do our inverse functions, we switch our domain and range. That's going to give me, these values are going to hold true on that domain from -1 to positive one. All right. We're not going to derive the other functions, but you would use a similar technique to derive the other derivatives of the other inverse trig functions.